Find the volume of the paraboloid z equals 3 minus x squared minus y squared, which is pictured here on the right, above the xy plane. All right, so we're going to make this into a polar integral. So the first thing we need is we need bounds on the polar integral. So we're going to have integral. We're going to have 3 minus x squared minus y squared, then dx dy, some order. We're doing it over the region, and the region is this circle where the paraboloid intersects the xy plane. All right, so to figure out how big that circle is, we say, okay, well, at the xy plane, that means that z is equal to 0. And so then the paraboloid, when z equals 0, that equation is 0 equals 3 minus x squared minus y squared. All right, so now rearranging that, we can move the x squared and the y squared to the other side, and we get x squared plus y squared equals 3. And then this 3 here is the radius squared. So that's actually going to mean this is a circle. X squared plus y squared equals the radius squared. And the radius of that circle is the square root of 3, right? Because this 3 is the radius squared. And you square root of 3, you get 3. All right, so it's going to be a circle of radius square root of 3, which makes sense here. The square root of 3 is about 1.7. So it's closer to 2 than 1 on each of the axes. And then it's going to be from theta 0 to 2 pi because you go all the way around. So then translating this, we'll get integral. All right, so we have to translate the integrand here. So we have 3 is going to stay 3. Here we have it's minus x squared minus y squared, or like minus quantity x squared plus y squared. I could put parentheses in there and put that in a plus. And so really that's 3 minus r squared. Right, and then I have to keep track here. And then the dx dy is going to turn into r dr d theta. You could have made it d theta dr if you want. It doesn't matter in this case. They're both constants. So the r bounds are going to be 0 to square root of 3. And then the theta bounds are going to be 0 to 2 pi for the entire circle. All right, so this isn't too terrible. So let's go ahead and get started. So 0 to 2 pi again. And integral 0 to square root of 3. And then multiplying the r through, we get 3r minus r cubed. And then if I want to be careful, I'll write dr d theta. All right, so I can integrate with respect to r. That doesn't look too bad. And I think I can squeeze it in here. So we get integral. We're going to have 0 to 2 pi because I'm going to complete integrating with respect to r. So 3r will turn into 3 halves r squared. Then minus r cubed will turn into minus 1/4 r to the 4th. And that's all going to be evaluated from 0 to square root of 3. Then I still have my d theta at the end. All right, then coming back down to here, so if we plug in square root of 3, this works out nicely because we have r squared and r to the 4th, so the square roots won't be in the evaluation. So let's see, integral 0 to 2 pi. So we've got 3 halves. Okay, we have, the 0 is going to completely cancel, right? We get 0 squared and 0 to the 4th. That's gone, so we just have to worry about the square root of 3. So square root of 3 squared, that's going to be 3. And we have a minus 1/4. And we have square root of 3 to the 4th. So that's going to end up being 3 squared d theta. All right, so let's simplify that if we can. Integral to 2 pi. All right, so let's see, that's 9 halves, and that's minus 9/4 d theta. All right, so that equals 0 to 2 pi. Okay, so 9 halves is 18/4. So 18/4 minus 9/4 is 9/4, I believe. All right, d theta. And then this is an integral that's about as simple as it can be, right? We don't have any variables in here, no thetas. It's just a constant. So what we end up with is 9/4 theta evaluated from 0 to 2 pi. So that ends up being 9/4 times 2 pi minus 9/4 times 0. So I'm not going to write that out. And that ends up being 2 cancels. We end up with 9 pi over 2. And that's how you integrate this paraboloid. It's really nice for polar because it's radially symmetric in both the surface that you're integrating under, and it's also radially symmetric in the region that you're integrating over.